So any questions so far? The discussion on the energy scales justified the picture that are drawn here. Okay, so of course you can take that as granted, granted, but it is better to have a better understanding, simple estimation, a little bit of quantum mechanics. You know, molecular allowed energies are spaced like this and in this pattern, and can be labeled by N and L. And hidden behind L, remember, there's still an M index in the YLM theta phi, and those are degenerate states. So let us move on. I mentioned that room temperature is 1/40 eV. So it is 0.024 eV or so. And usually it is smaller. KT is much smaller than the spacing between vibrational states. So n equals 0, n equals 1, h bar omega is something like 0.1 eV. And now you use KT or thermal room temperature thermal energy, try to thermal excite something up. The percentage is tiny, tiny, tiny. If you want to look at how tiny it is, go to sample question 26 this week. Okay, the TA really plugged in some number and show that basically at room temperature, all the molecules are in the n equals 0 vibrational ground state. However, remember, belonging to the vibrational ground state, there is a set of rotational states there, labeled by L. The typical energy here is 0.001 eV. Thereby, room temperature is actually bigger than that typical scale. So you need to exercise Boltzmann factor, the exponential minus energy over kT. That will give you how many molecules will be in different rotational state labeled by L. Okay? So here, before we move on, this is high school physics, but I think it is good enough for year 3 students to know, okay? Because there are different units being used, and you have to live with it sometimes, because the people doing spectroscopy usually give you a graph. The axis is centimeter inverse, the wave number, okay? Basically, it means in 1 centimeter per centimeter, right? So centimeter minus 1, how many wavelengths are there? So it means something like that, okay? But then sometimes it is wavelength, and sometimes it is joule per molecule, sometimes it is hertz, sometimes it is frequency times 2 pi, okay? So angular frequency, so things are complicated. So have a little bit of sense out of it. So microwave, that will be rotational spectrum. It is in this range, terahertz, lower or slightly lower, okay? Terahertz things is now very popular in different research areas. And then wave number, you know, microwave oven, you put it in your kitchen. So it's that big. So wavelength is about that big. Makes sense, huh? Okay, so centimeter or even a few, you know, that, you know, you put a chicken in the middle, you want some standing wave to form there. Okay, so reasonable, ballpark. Okay, physics of ordinary life. Okay, so and then in our context, it is related to rotational motion of molecules. Going up in frequency, we have far infrared. Then it is terahertz to 10 to the 13 hertz. This is the wave number. And then it is related to rotational motion of smaller molecules, okay? Because the moment of inertia is smaller, this energy scale is slightly higher. Next, go up in EV, it is infrared, then you start going into the boundary of visible, okay? So it is 10 to the 13, 10 to the 14, this is wave number, and then it is related to vibrational motion of flexible bonds, meaning that K, rather loose. It could vibrate readily. Okay. Then going higher, it is visible to ultraviolet. Visible is about 10 to the 15. So it is about this range. And then this is the wave number. Now this is power, very many different of what magnitudes here. Okay. And then it is related to electronic transition, go up there. All right. But usually we will not consider this kind of transition here. So with this idea, we can move on to some discussion on transitions. The first thing we will discuss is rotational spectrum. It means the following: only transitions between rotational states belonging to the ground vibrational state are involved. That is usually the case if you shine in microwave frequency EM waves. I already explained that room temperature, usually a gas of molecule can only occupy vibrational ground state. And then if you only put in a little bit of H nu, not very high energy, molecules cannot take this microwave incident energy to go to the vibrational excited state. So all they can do is to make transitions between L, okay? So N is 0, transition between different L's that gives rise to rotational spectrum. With this, we can study or extract some information about the bond length, because the moment of inertia is related to that. The reduced mass, if you know what is the molecule, usually you can estimate it or you can calculate it more accurately. It is given by 1 over MA plus 1 over MB is the reciprocal of the reduced mass. Think about it, if one is light, hydrogen, one is heavy, okay, then the lighter mass will dominate this reciprocal, the sum of the reciprocals, right? So therefore, if you have a HCl, hydrogen chlorine, then the lightest thing is hydrogen, and the reduced mass is quite close to hydrogen photon mass, or the mass of a hydrogen atom, okay? So if you don't have time to use the formula, then be clever. If you see one is very light, that will dominate, you just assume this is quite okay, all right? So now, if you plug in some typical 1.3 angstrom equilibrium separation, and then use hydrogen, reduce mass, etc. As already mentioned, the typical energy is 0.001 eV. So what we are considering now is quite simple. It is related to transitions between these sets of states. Okay? Again, I must say that this sketch is highly exaggerated to make sure that you can see them. On the same scale, they should go very close to each other, all right? So blow it up, it is something like this, all belonging to the ground state of vibrational levels, all right? Now, let's look at what transitions energies will be involved, okay? So let's say 0 goes to 1, differ by L by 1. There is some selection rule, I will tell you later. Let's say it's delta L is 1. So you have this difference, and then that looks bigger. This looks bigger and bigger, all right? It's L times L plus 1 for the energy levels, but what are the differences? Very interestingly, this minus that is h bar over I, okay? And then you have 3 of this minus 1 of this. This is double that energy. This is 3 times 6 minus 3. This is 10 minus 6 is 4 times, and so on, okay? So here, I list the energy out, and then the difference turns out to be regular. 1, h bar over I, 2, 3, 4, 5, and so on. So the rotational spectrum is expected to show a series of equally spaced lines. This is a transmitted intensity, meaning you shine something, microwave frequency, a bunch of different frequency range into it, and then look for what is missing, what frequency becomes less intense after the EM wave go through the sample. So you see dips in the transmission, meaning the energy is lost to the molecule, so absorbed, okay? Make a transition up. The point of the discussion here is that the energy to be absorbed is a multiple of h bar over I, all right? So you see this kind of pattern. Rather regularly spaced, okay? That gives us one way to extract useful information. For example, if you can read out this regular space, then you know h bar over I. Therefore, you know I. Therefore, you can get the equilibrium separation from rotational spectrum. That is a very useful piece of data for a molecule, right? Okay, so do you understand? Do you understand? You will see regular things, okay? So technically, you may do something like this. I read out the range of several peaks and then divide it by 3. All right, then you may get a better number, and then you get a more accurate R0. That's pretty easy, right? And microwave frequency is not expensive. I mean, you don't need a lot of research funding to buy an apparatus. Well, you have a microwave oven at home, only a few $100s. Okay, here I invoked a selection rule. Delta L is plus minus 1. I will have a little bit more to say later. Here is another example, carbon monoxide. This is rotational spectrum. By that, I mean the experimental work is done in the terahertz frequency range. Okay, so here you see, this is terahertz, 10 to the 12 hertz, okay? So this is in the range of microwave range. This one is not a transmitter thing. It inverts the analysis, then it is the absorbance. How much is absorbed? So it's the same as how much is missing, okay? So again, you see, quite evenly spaced line. So if you can read this thing out, or you read several things out and divide it by 4, okay, then you will get a value for h bar squared divided by I. Now the trouble comes. You must be very careful about what is the axis here. Now, I already told you, sometimes it is, this one is frequency, then someone will give you centimeter -1, that is the wave number, someone will give you electron volt, that must be a physicist doing that data and so on, okay? But the concept is simple. Evenly spaced line, when the x-axis refers to something that you can convert into energy, photon energy, okay? The spacing is h bar over moment of inertia, h bar square over moment of inertia, and therefore you can extract moment of inertia, therefore you can extract equilibrium separation. That's it. Now, I know that many of you are taking Professor Swegold's thermal and statistical physics. Then you may be wondering what happened to this shape. Okay, so this is what we call the envelope in this spectrum. Like a bow, okay? So I sketched the envelope here, and then you may want to think about what is the physics here. Okay, now it is related to statistical physics. Basically, it has 2 contributions. One contribution is an increasing line. Okay, let me tell you, this is related to 2L plus 1. Do you know what 2L plus 1 is? This is the degeneracy. Okay, the higher the L, although you see only one line behind which there are more states the molecule could go into. There's another line coming down that is related to something like E minus do you recognize this as something like the Boltzmann factor? Okay. And you multiply this thing together, you get some kind of an envelope function that shape. So this is related to statistical physics. Basically, it means the following. We already mentioned that at room temperature, molecules could populate these levels, and then the absorption or transmission spectrum must reflect how many molecules are initially in this state, in this state, in this state, and so on. Okay, and that is why you have this envelope. But that is not my duty. You have another course. I just want you to make connections. Here, let us discuss why do we have this selection rule, and then are there additional requirements for the molecule in order we can see these rotational transitions. No new physics here. We have done time-dependent perturbation theory, a lot of derivations. At the end, we know what is critical for transitions, right? So for transitions, we need a mechanism. The leading or most important mechanism is electric dipole moment. In an atom, the nucleus is just, there's only one nucleus. We relied on the electrons' dipole moment, okay? But here, we have a molecule. So we have A and B nuclei. If the charge are not evenly, I mean the electron bonding are not evenly divided, then this molecule will have permanent electric dipole moment, all right? If B is slightly negative, A is slightly more positive, you will have an electric dipole moment pointing from negative to positive ions. You know that in electromagnetism, all right? So in molecules, again, we need to consider electric dipole moment, but this time it is the molecule one, usually dominated by the uneven bonds. The electrons wave function shift to one side, you have this ionic character, okay? So we assume that there is some electric dipole moment of the molecule, and then that's fine. We dot it into the incident field. We start doing time-dependent perturbation theory. After 10 pages, we have an integral determining whether this is allowed or forbidden transition. So we pick that up from that point. So we have an integral. It should be R theta phi as well, but here we only care about the theta phi integration. So you have, if you have an electric dipole moment, there will be a direction. Then you have a E field. You can set it as the Z direction. Then it has to do with a dot product, okay? So therefore, it picks up this thing, projection into what you call the direction of the field. That will pick up a angle cosine theta. Then you have an initial state of rotational state that is YLM theta phi. And then you have a final state that is YL prime M prime theta phi, all right? The vibrational states are the same, so I don't need to worry about that part. That is non-zero, so that will determine, this one will determine whether it is zero or not, okay? So we have a mu here coming out, we have a field here coming out, the dot product pick up an angle. Well, we have considered this previously in the transition between electron states in atoms. This thing works like a Y1. Okay, so Y11, Y10, Y1 minus 1, depending on it is cosine theta or sine theta, cosine theta, things like that. Okay, nonetheless, when you see cosine theta, I hope that you know Legendre polynomial cosine theta, P1 cosine theta is cosine theta. You know that, right? And Y1 is related to P1. Okay? So once you realize that what you pick up in the middle is like a L is 1, then using spherical harmonics properties, you have 3 YLM multiplied together, the L index should add up, okay? So once you have a 1 here, therefore the delta L must be different by plus and minus 1 only, okay? So this is the selection rule. But pay attention here. there is an additional requirement. At the outset, we need a mu to be non-zero here. That is to say, the molecule, diatomic molecule we consider here, must have a permanent electric dipole moment. Okay? Now, that is not the case for O2, oxygen, because they are the same. The electron will not bias which side, right? It is not the case for N2, nitrogen. It's not the case for H2. Okay? For those, you cannot do microwave and get the experiment and get the microwave spectrum. Okay? You see, that's why I show you carbon monoxide. They are different. Then they are sensitive to this prop. Okay? So this is an additional requirement in molecular physics. I already mentioned this several times. We can use this rotational spectrum to plot or to extract the equilibrium separation or the bond length. And in astrophysics, radio telescope, probe around this range, okay? And this microwave probing is also being used in astronomy. Next is a little bit technical jargon, because sometimes you need to look at real spectrum, depending on the future work that you will do. It is just a way to express the answer, okay? So now we know that rotational levels is given by that. And many don't like H bar. Well, physicists like H bar, but all the other people like H. So you just write it out. No new physics. All right. And now, don't want to carry that much thing with you, then you call it this combination, 1 factor of H divided by 8 pi square I, okay, and I has mass and R square in it. Nonetheless, if you factorize this thing out, this B must be a frequency, right? This is an energy, H nu is a frequency, so B is a frequency, okay? Now, this B contains the molecule's information along with some fundamental constants. It has a unit of Hertz. This is called rotational constant of a molecule. You can look at it at data books. Different thing, they will give you a number. Okay? You have to check what units is being given. If it is given in Hertz, it is referring to this thing. Okay? But the physics is the same. If you express it this way, the transmission thing will be, again, evenly spaced. Only the spacing between two dips, okay, is now 2 B's. Well, you can work it out from here, all right? So, again, the same game, someone give you this, and this is Hertz, okay? And then you can read out this thing. This is 2B, and 2B is twice of this, and then you can extract out 0 out. Same thing. The only information here is that don't be scared off when you talk to chemists or spectroscopists. They use, I give you the rotational constant. Don't worry, it's just the same thing as we discussed, okay? Next page is even worse. There are 2 things called the rotational constants in textbooks and the literature. Again, you need to live with it, okay? They are the same thing, but off by a factor of 1/c, the speed of light. What for? Because many spectrum are given in centimeter -1, the wave number, okay? So when you turn the energy, this thing, okay, into something hc times something that is wave number, this combination is an energy. Okay, then this h bar again is bad enough, called rotational constant. Therefore, when you look at data book, you better look at what this rotational constant, what is the unit given there. If it is in wave number, then it is this particular combination with an additional c there. But again, don't worry, no new physics. If you are given a spectrum like this, it will be, there will be evenly spaced dips. The separation between two dips is 2 times b bar. Then you start analyzing, okay? So again, the point here is don't be scared off. That's enough for rotational spectrum. Let's move on, transitions between vibrational states. What we are talking here now is from here to here, okay? But once you have this, life is more complicated, as you can imagine. Because when you go from n equals 0 to n equals 1, behind, there may be another label, L, being changed. For example, n equals 0, L equals 0, go to n equals 1, L equals 1, because there's a selection rule for L, right? Plus 1, okay? So not only will the vibrational index be changed, the L index will also be changed. You go from one member of a family n equals 0 to another member in the n equals 1 family, okay? When that occurs, you have vibrational rotational spectrum. I hope that you understand the name now, because both n index and L index will be involved in such a transition. Okay, so that is the big picture. To remind you, typically the spacing is in the infrared, 0.1 eV order. Okay, so you shine in infrared light, you may induce transitions from here, somewhere from here to somewhere in there. Get me? And then we hope that using IR spectrum, there's something related to K that can be extracted, therefore we can get the spring constant, okay? So let me give you some data so that you have a better idea of the energy scale or the frequency scale involved. So diatomic molecule, the electrons form the bond. We model it as a spring constant. So we have this frequency. So how big is this K typically? So the table shows you some real numbers. So here are again some diatomic molecules. Okay. Again, you see that two atoms are different, so that can be easily responding to incoming infrared frequencies with transitions allowed. The typical frequencies here, I mean, this is mu. Okay, omega will have a 2 pi difference. So this is nu in hertz. So you see all this resonance, or the something like an oscillator, at around the same ballpark, 10 to the 13 hertz. Only this slightly different, and then it all falls into 0.2 to 0.4 eV range. So that is the real thing. And using this, and you know the mu, so after give you HF, you know the mu, you can estimate the spring constant. And this is how the spring constant of a chemical bond, that is the number, the order of magnitude. And for those of you who want to have some ballpark range in your mind, here I try to give you one example, give you as many possible units as I can. So 5 times 10 to the 13 hertz, that is frequency. It is 50 terahertz, another popular name. And then it is 0.2 eV, all right? That is physicists, physics students' preferred unit. And then it is 6,000 nanometer, this is wavelength, or 6 micron wavelength, and then even worse, 1668 wave number, okay? So if you want to go into this business, believe me, if you go into labs, usually in material science, in solid state, optical probe is very popular. So once you get in, you have to live with it. So now we need to consider when could this transition between vibrational state happen, okay? Will there be some physical requirement? And with this, what is the selection rule, okay? Now, the physics is quite interesting here. We want to have transitions. The most important thing, mechanism is electric dipole moment, okay? So first of all, you may think, the molecule should carry an electric dipole moment to start with. That is partially right in this case, all right? Let's see. In vibrational transition, actually we need one more requirement, as we will see the reason later. What we need is the following. As the molecule vibrates, as I shown here, okay? Relative motion, the B is vibrating. We also want the following thing to happen. The electric dipole moment has its magnitude varying as the vibration goes. Now, that is different from having a constant, permanent value, fixed value of electric dipole moment. That is what we need for the rotational case. But in this vibrational case, it is a little bit more. When the molecules vibrates, we also need the electric dipole moment to be changing as it vibrates, okay? So if you have B is more negatively charged, A is positively charged, then in this case, you do have a varying magnetic dipole moment as the molecule vibrates. Now, let's look into the reason. For transition between vibrational states, the initial state is an oscillator wave function, but centered at equilibrium separation. Final state, another oscillator state, and then we will have this energy, a perturbation, minus mu dot the field of the incident EM waves. Now, this thing, as the molecule vibrates around R0, we could expand it into a constant that is the permanent, if that is the rotational thing, okay? So separation times the difference, slightly difference in charge. That exists, okay, but we also want the first derivative to be non-zero, and then times R minus R0, okay? Now, this is the thing that I mentioned. It should have a derivative d mu dr. That is to say, as R changes, mu changes with it, okay, about that particular point. And we need this in order to induce the transition between vibrational state, okay? Why is it so? Because if I plug this into here, only keep the permanent term, this is a constant, it goes out. This is a constant field, it goes out. The theta phi part has nothing to do with the oscillator state. That is the angular thing, all right? Therefore, you will have two different vibrational states integrate over. That is zero. You don't have this transition, okay? So in order to induce this transition, you need this term not to be zero. This term not to be zero means you need this not to be zero for the molecule. Vibration, as the molecule vibrates, the dipole moment changes, okay? If this is not zero, that will come out. You pick up this difference, you have this in the middle. Once upon a time, problem set number 2, you have done this. This is non-zero. Delta n is plus minus 1, right? Okay, so no new physics, provided that you know how to apply them. So here, no new content, but we apply it to a new context of vibrational level transition in molecules, okay? So that's why we have this selection rule, but one more requirement. The molecule needs to have the electric dipole moment changing as it vibrates, okay? Diatomic molecule, if the charge is not evenly divided, then you have this case, okay? I hope that you know from your classical mechanics course. Diatomic molecules only one normal vibrational mode, okay? That is vibration. Okay. How many of you know this? Okay. Now, you have two atoms. Okay. Therefore, you need x1, y1, z1, x2, y2, z2, 6 variables. But people call it degree of freedom. That is too much a jargon. Just you need 6 numbers, okay? Then you have a center of mass motion singled out, factorized out. Center of mass take care of 3 of them. 6 minus 3, 3 remaining, all right? Now, diatomic molecules is 2 balls with a rod. 2 balls with a rod in 3 dimensions. The orientation will take 2 angles, theta and phi, okay? So in order to specify where does it point at, you need 2 numbers, 2 variables. So you have 3 remaining minus 2, you only get 1 left. That is the vibrational degree of freedom, okay? That's why for diatomic molecules, we only have 1 omega, and we always think of it as this, okay? Now, the case will be different when you have CO2 or H2O. Okay. Now, in these two cases, do the counting. Okay. You need 9 numbers, 3 atoms. Okay. Then center of mass, take 3. Okay. Now, take CO2. It's linear molecule. The orientation will take it 2 angles. You have 4 vibrational modes. Okay. Now, students, you better do the counting first before you start writing down Newton's law, M1, M2, M3, and then do all the set up the Newton's law and then do normal mode analysis, find the normal mode frequency. Okay, you do counting, you know how many you will get. All right. Now, for CO2, 4 moles. You look it up, Google it. People will tell you, there's some stretching mole. Okay. Carbon to oxygen horizontally go out there. Do you see? Okay. Now, let me tell you. CO2 with distance, the electric dipole moment is not changing as this vibration goes on. Okay. So this particular mole cannot respond to infrared excitation. This is called infrared inactive. Okay. Now, I will have to stop here today, but I make this remark just to make sure that you understand. This statement is not useless. It is a useful statement when we go into molecules consisting of more than 2 molecules. That is to say, away from diatomic. Okay? Now, diatomic is simple. O2, of course, there's no magnetic dipole moment to start with. Okay? Then you don't have all this discussion. Okay? But in CO2, in H2O, things like that, there are some vibration that could respond to infrared excitation. There are some vibrations that are not responding to infrared. Okay? Unfortunately, for CO2, next time I will mention it, there is 1 mole respond to infrared, and that is responsible for trapping the infrared radiation that the Earth wants to give out, and it is called greenhouse gas, and we have too much CO2 as well as methane and also water vapor in the atmosphere that, you know, everybody in the world is now discussing how to reduce carbon emission, and that is quantum mechanically, that is one particular vibrational mode responsible for making CO2 a bad molecule. All right, so I will discuss it next time after a few days of Easter holiday. Okay, so I will stay around if you have questions. Otherwise, I will see you next week.